I hope everyone's doing well this morning. Thank you for joining me for this video where we are looking at now the next peculiarity, the second order linear homogeneous differential equations where you have one real root. Keep in mind, as I presented you, this represents a linear homogeneous differential equation of the second order. You have a second order derivative, but everything is here nice and easy, generalized in a linear format equaling a zero, hence it's homogeneous. One real root, you're looking at a quadratic equation, the b squared minus 4ac, the discriminant equals 0, you have one real solution. Technically you have two solutions, but they're identical, so it's one real solution. Hence, we're looking at that peculiarity. Keep in mind what we've seen in the previous video where we were looking at two real roots. Everything develops from the same exact procedure with a difference at the very end. Let's show you two examples for this because this is not overly hard. Let the first example we look at is just y double prime or second order derivative of y plus 6y single prime first order derivative plus 9y equals 0. We have to solve this second order linear homogeneous differential equation. You know already y is equal to e to the rx. Your y prime is equal to r e to the rx. Your y double prime is equal to r square e to the rx. Now some people use different terminology, m's versus r's. I like to use r. You bring in these substitutions, you're looking at r square e to the rx plus 6r e to the rx plus 9 e to the rx is equal to 0. You isolate your e to the rx, you're looking here at r square plus 6r plus 9 equals 0. I've shown you that you can just eliminate this and there's nothing wrong with you doing that, and you would factor this out. When you do it, what are you getting here? You're getting r plus 3 times r plus 3 equals 0. You're having r is equal to minus 3 and minus 3. Hence, you have one different real solution, even though you have two solutions, but they're identical. You can bring them in this general format here, a e to the minus 3x. Remember, these are your r values. They're coming here, rx, the r being replaced by your actual value, plus b e to the minus 3x. You see, they're identical. It doesn't make sense to present an answer like this because technically if you did the substitution that c were equal to a plus b, hypothetically you did this substitution, c is equal to a plus b. Remember, you can use different constants. You can use c1, you can use c2, you can use c3 for this. This would be your c1, this would be your c2. It depends on your convention. I like to use a, b and c. If hypothetically this is what you're doing, then you're looking at y is equal to, you would isolate here e to the minus 3x, you would have a plus b. And then you would of course bring in the substitution, you'd have e to the minus 3x times c, which you would write in a better way as c e to the minus 3x. And this could technically represent as what this, your generalized solutions of this differential equation right over here. However, there's a problem here. Since you're looking at a second order differential equation, you must have two arbitrary constants. If you go down this route, you're only presenting one constant. If you're going down this route over here, you're presenting an answer which is generally acceptable, but it's not the best answer. Your best answer is now the procedure I will show you, or the mechanism I will show you, which is how you will present these type of answers for second order linear homogeneous differential equations where you have one real root. And your template will differ, or your template will modify. Your template will modify such that you will have this type of template, a e to the rx. Notice I'm using r and I'm putting here r1 plus b. Now bring in an x, e to the r, let's just put 2x over here. That's a generalized template form. I have an r1, I have an r2, they ended up being identical. When they are identical and you're looking at this scenario, this answer here will modify by means of this template here to this. Y is equal to a e to the rx, which is minus 3x, plus b x e to the minus 3x, and that right there is your final answer for this. This right here will represent your generalized solution to the differential equation where you have one real root. You have two solutions, but they're identical. Technically, you have one real root. You can, if you choose to present this in a further simplification, y is equal to e to the minus 3x, and then you isolate as you have, and then you bring in a plus bx, and that can be yet another varied form of that. You're just simplifying this by means of isolation. Both of those answers are acceptable. This right here is the least acceptable. These two here are the most acceptable. We will look at one more example for this particular video. This right here represents our last example for this video. We will have one real root come about. You will have two solutions, but they'll be identical. You have this second order derivative plus h times first order derivative plus 16y equals 0. It's a linear homogeneous differential equation. You'll bring in these substitutions. You're really looking here, r squared e to the rx plus 8r e to the rx plus 16 e to the rx equals 0. Bring in the erx isolation and you have r squared plus 8r plus 16 equals 0. This we will zero out, and here when you factor this, you're looking at r plus 4 times r plus 4 equals 0. You know you're getting r plus 4 whole square, but you're having identical solutions. R is equal to minus 4 minus 4. Your least acceptable form of answer is a e to the minus 4x plus b e to the minus 4x. That's the least acceptable. You should not even present that. I'm only putting it because this is how you would present your answer based on having two real roots, which were different, but that's not our case. Your best answer is this: a e to the minus 4x plus bx e to the minus 4x. If you want to take this one step further, you can isolate the e to the minus 4x and you're looking at a plus bx. And that right there, either of these are your answers for that differential equation, the second order right over here. And this question has been solved. As a side note, I won't show you any derivation here, but I'm just showing you as a side note over here. The reason why this thing works over here, we are bringing in the x over here, is because for these type of equations, you can show, I'm not showing it to you here, but you can show that kx e to the minus, well, let's just say rx is a form of this type of differential equation. You see how you're having the constant and the x, and you can bring this into the picture. You can show that this right here is a solution to this style of differential equation. Hence, you're seeing something like this. Except here we're looking at bx, but you're seeing the exact same representation. But keep this in the back of your mind. Anyhow, we've looked at two examples here where we had two solutions, but they were really identical. Hence, you're looking at the one real root, the b squared minus 4ac equaling a 0. And you'll see that to be the case. B squared minus 4ac equals 0. Here's my b. You'll have 64 minus 4 times 1, which is your a, times 16, which is your c value. You have 64 minus 64 and it equals 0. Indeed, we have this specific format coming into play, and you will remember this template now. When you have one real root, you're looking at something which is a e to the rx plus bx e to the rx. These will be identical r values because you have two identical solutions, but they count as one real root. Thank you for watching this video. Have a good day.